Hi everyone, this is Explore Algos and today we will discuss a research paper published by Google in 2003. It's based on MapReduce, Simplified Data Processing on Large Clusters. So this is a very famous paper that was published in 2003 and today's Hadoop is basically built on this idea itself. So let's discuss this paper. MapReduce is basically a paradigm or it's a programming model for processing and generating large data sets. So Google has a very large amount of data and Google also have many business use cases like processing data on a very large scale. For example, building search indexes, performing distributed sorting, or doing a URL count to find out the most popular or the most clicked URLs in the search services. So this type of programming paradigm helps with two things. First, it helps with parallelism, and second, it helps with data locality. So what is parallelism? We can understand this with an example. So let's say we have our files or our data that is stored in a distributed file system. So MapReduce uses a distributed file system. This is an in-house file system developed by Google known as GFS, Google File System. There is also a paper that very well explains the internal architecture of GFS, and MapReduce uses that underlying architecture. So we have this input data. We split this data into the multiple chunks, K1, V1, K2, V2, K3, V3. These can be considered to be present on different separate machines. By machine, we mean that physical servers that are independent and they are apart from each other. Now we can run certain mapper tasks in parallel that will perform some mapping operation on these input data independent of one another. They can operate on this data independently and also parallelly. That means that we can run multiple tasks on these multiple data inputs at the same time. This is what we mean by parallelism. So the MapReduce enables parallelism that allows us to perform a lot of operations or the computations in a reasonable amount of time. Now the second is MapReduce also uses data locality. So let's say we have these mapper workers and these are present, or they basically run on commodity machines which are cheaper physical servers, and data locality means that the data is locally available on these machines. So in MapReduce, as we will discuss it in more detail later, that there is a master node that is responsible for allocating work to the different workers. Workers are nothing but the different physical machines. And the work that is being allocated is done in a way so that these workers can access the local data they need for processing from the local disk of that physical machine. And they do not have to fetch this data by making a network call from some other machine. So this is data locality. And it makes a significant difference in the performance and the successful it's also one of the reasons why MapReduce was successful in Google, is because it's basically very fast and they're optimizing a lot on avoiding network calls and doing a lot of offline processing. Now, how is this enabled? We have already discussed it, that underlining the MapReduce, they are using a distributed file system. It was developed in-house by Google, which is known as GFS. There is a very popular paper out there that you guys can read about it. Now, what is the purpose of the MapReduce? The MapReduce was basically built to keep in mind, the idea was to build an abstraction layer so that the developers can focus more on the business use cases like processing of the, like performing certain type of operations, instead of focusing more on building distributed systems and all the things that are needed while we build a distributed system. So MapReduce is a library or a framework that provides this abstraction. So developer need not worry about the data partitioning. That means how this data is split into the multiple chunks. Developers who are using MapReduce do not have to worry about this. The second is the handling of the machine failures. As this is a distributed system, MapReduce, and there are multiple machines, hundreds of machines or thousands of machines running in a cluster, and network failures are bound to happen. In that case, how the machine are recovering from those failures and how MapReduce is fault tolerant to those failures, that is taken care by this MapReduce framework, and developers as such do not have to worry about how to handle any machine failure. Now the load balancing, how these tasks will be distributed among these different hundreds or thousands of machines on a cluster, that is something that MapReduce library takes care of, and developers as such do not have to worry about this. So as you can see here is that the job of the developer is now only is to write these mapper and reducer operations. So let's understand this programming model in the terms of input and output. Now there are two main tasks. One is of type mappers and the another is reducers. The mapper functions takes a key value pair of this form K1 V1 and it produces zero or more intermediate key value pairs that can be of the form K2 V2. We'll understand this with an example later. And now these intermediate key value pairs are grouped together based on the key. And they are converted into a format of the type. All the values that belongs to the same key are put in a list and a key value pair is formed for this particular data, and then this is passed to the reducer function. The reducer then takes these key value pairs and it can perform any type of operations on this list of values based on the business logic. And developers only have to worry about defining the mapper functions and the reducer functions. Developers do not have to worry about grouping, how all of the groupings of these values is happening behind the doors. So this is all handled by the MR framework. Now let's take an example of our word count. In the word count, we can define our mapper that it is taking a string key and a string value. The key here is a document and the value here is this content of this document. So the key can be unique, it can be the document ID. Now for all the content in the document, because it's a string, we can go word by word in the string, we can sanitize it, tokenize it. And then for each word in that particular content, we can emit an intermediate word count of 1. That means this line basically means that we have seen this word one time in this particular document ID. Now the reducer operation will be simply a string key and iterator values. This iterator values is going to be a list of count values. Let's understand it with an example of a word count. In word count, our mapper function can be something like this, a string key and a string value. Now this key is a document ID. And the value is the content of that document. Now we can sanitize the document, we can tokenize this into a list of words, and for each word we can emit a value of count 1. So this is basically a key and this is the value. Now in the reduce phase, we can take this key. So let's say we got these things. We got A1, B1, A2 in the first phase of the mapper. Now the mapper emits A1, B1 and A2. Now the MR library will group together the values for the same key. Now it will be formed in the form of a list and it will be something like this. Now this will go as input to the reducer. The reducer, this is an iterator. Here this is an iterator because this list can be really big, that it do not fit into the memory. So it's kept as an iterator. Now we can scan this list, and for each count we can add it to the result and we can emit a value that for A the count is 2 and for the B the count is 1. This is basically a very simple demonstration of what will happen in hundreds or thousands of the nodes when we have millions or billions of documents. Now there are some other examples as well, like counting of the URL access frequency. So we can count how many times a particular URL was accessed, or we can also build our search indexes, which are nothing but inverted indexing using the MapReduce paradigm. And this is something that is also done by Google in production. The paper described it very beautifully. You guys can also look into it and read about it more. Let's discuss the implementation of MapReduce framework. So Google used dual processor Linux OS 2 to 4 GBs of machine, and it uses commodity servers with a network capacity of 100 Mbps to 1 Gbps, and machine failures, as there were hundreds or thousands of machines in a cluster, they were very common, and the storage of the input data is provided in the inexpensive disks directly attached to the machine. They are non-volatile in nature, and a distributed file system was used to manage the data on the disk. Now, the user's job was to submit the MapReduce jobs to the scheduling system and define the mapper and the reducer operations. So the input data was split into the M splits were made to the input data, and the M was uniformly distributed among the different mapper workers. Now let's say that we have mapper machines 1, 2 till M, and we are getting one piece of input data and giving it to each mapper. Each mapper will be performing some operation on this data independently and also parallelly, and will produce the intermediate key value pairs. Then these key value pairs are written in the local storage of these machines. So the mappers will store the output of the intermediate key value pairs in the local disk temporary files. We'll discuss more about it later. And the mappers are also responsible for sharing this information with the master that, hey, I've stored all these output files on my local disk at this particular location. Now, then it's the responsibility of the master to inform the reducer workers and tell them where to get this data from. The reducers are then responsible for fetching the data from this local location. and produce their outputs. The reducers will get this data after the keys and the values are combined and processed, and the reducers will perform their own operations. Now the mappers are basically keeping our temporary files. Because we are splitting all these intermediate input space into the R pieces. So each machine will keep R files, local files, and then the reducers will get all these files from all the mappers. Once the reducers have all the data, the reducer is then responsible for merging and sorting of that data so that it can perform its operations. And how are we splitting these intermediate values into R pieces? Based on a partitioning key. So let's discuss this step by step. Now the step 1 here is that the input file is divided into the M pieces of chunks. Now each chunk is 16 to 64 MB per piece. Now there are multiple copies of the MR program running on multiple machines in a cluster. And in the cluster there is one master node and rest of them are the worker nodes. Now the master node assign a machine either one of the M map task or one of the R reduce task. That is, it is the job of the master node to assign work to the worker nodes. A worker is then assigned a map task. Any worker that gets assigned a map task will read the input files, will read the data from the input files, and it will produce the intermediate key value pairs, and it will save them in memory. First it will save them in memory and then it will flush it out into its local disk. Now periodically buffered pairs are flushed onto the local disk, partitioned into the R regions based on the partitioning function, and the location of these is passed to the master, and the master will then send this information to the reducer workers. The reducer workers will read the data, group them by the same key and sort the data. Once they have all the data sorted, then they will perform the reduce functions and produce the output. The output will then be stored in the global output file systems, that is on the distributed file system, that is on GFS. Now let's discuss the master's data structures. Master is keeping track of a few things here. So master is keeping track of how many workers are working and what is the state of each worker. So master will ping periodically to all the workers to check if they are in an active state or they are idle or they are not responding. So for each worker ID, the master will keep track of their current state. Now master is also responsible for keeping track of all the tasks and the status of these tasks and the worker ID if the tasks are in progress states. So for each task, it stores the state and identity of the worker machine. Now, for each completed map task, the master stores the location and size of the R intermediate regions. So, when a map worker completes a map task, it will produce R files. All these R files are also stored and maintained by the master. So master will keep a table of the size M into R. For each mapper, there are going to be R files, and it will keep track of the location of these files. So now let's understand what will happen in case any of the workers fails. So let's say the worker 2 fail here. So in that case, all the map tasks that were completed by the worker 2, they will be rescheduled. And what is the reason for that? Because the map task outputs are stored on the local disk of the same machine, and if that machine is not responsive, in that case we cannot access its local disk and get the data out. So in that case, what we need to do is we need to reschedule that same task again on some other machine. And for all the other tasks that are in progress, their states are reset to an ideal state so that they are eligible for rescheduling. Now what happens to the completed reduce task? As the output of the completed reduce task is present on the GFS, on the global file system, and not on their local machines, in that case we do not need to redo the same step again. Now what happens when a worker fails, the master will assign that work to some other worker, and it will also notify all the reduce workers to read the data from the mapper worker A than on B if the worker B was down. Now what happens if the master fails? In the case of the MapReduce framework, there was only one master node. That means that there is a possibility if that fails, things may go wrong. So in that case, the master keeps track of checkpoints or keep an AOL, that is an append only operational log, and keeping the checkpoints. So in case the master fails, master can come back again and it can restore its state by reading these checkpoints or its own logs. This concept is very fairly explained in the GFS paper. I would highly recommend you guys to read that paper also, and it would be very clear of how this checkpointing and the AOL or the operation logs can be used to recover from a master failure. Now what happens in the presence of the failures? The mapper task produces or maintains R local temp files on their local disk. Now, when this mapper task completes, it will notify the master about the locations of these R files. The reducer task will maintain only one temporary file for each reducer task, and it will, on completion, it will rename that file to the final output file that will be on distributed file system. Now let's say we are keeping redundant reducer task. We have two different machines that are performing exactly the same task. Now they will be maintaining a local temp file, and on completion they will be renaming the same file. So we will basically be renaming the same file, and the atomicity of this operation is basically guaranteed by this distributed file system, the underlying file system that is being used here. That basically guarantees that this renaming the same file won't have any conflicts. Now, as we discussed earlier, that in our MR job, we need to decide the M and we need to decide the R. That means how to split the input data into the M pieces, and how to split the intermediate key value pairs into the R pieces, and how large can these values really be. So the master makes big of M plus R scheduling decisions for each map task, and for each R reduce task, the master needs to allocate some workers and schedule these tasks. So there are big of M plus R decisions on the master. Also, master needs to keep track of the locations of each of the R files for all the map tasks. So that is big of M into R states, as we discussed previously. All of this data is stored in memory. Here the M is basically provided by the user, and R is also constrained by the user, because how many output files to create for the MR job, it's basically constrained by the user. If user wants only one file, we can keep one, otherwise we can keep it distributed into the multiple files. Also, the M here can be greater than the number of mapper machines. What does it mean? That one mapper machine or one mapper program running on a physical machine can basically be responsible for running multiple map tasks. This helps in load balancing. Now there are also some performance tweaks that are explained in that paper. We'll discuss all these very briefly, and these were attempted to speed up the program and avoid any performance bottlenecks. So one of them is choosing the partitioning function or the partitioning key. Where do we need partitioning key? As we discussed earlier, that when we create our intermediate key value pairs, we have a lot of key value pairs and we need to group them by some key. Now here we have all these intermediate key value pairs, and we want them to be mapped to a space of R pieces. In that case, we apply a hash function. So the default hash function can be something like this, hash of this key mod R. But if you want that, let's say you have these URLs, and if you want that all the URLs that belongs to the same host should end up in the same output file, or say, that should belongs to the same reducer, then in that case you can keep the partitioning key on hash URL host of that key. That means you have a key, you find out its host, and then you hash the host on the mod R. What does it mean? That if you have multiple URLs and you are now mapping them to a particular host, and all the keys that belongs to the same host will now end up in the same reducer worker operation. Now the second thing is ordering guarantees. So within a given partition, the intermediate key value pairs are processed in increasing key order. That is something that we can keep as a restriction, that to maintain the ordering guarantees, that when we are partitioning this, when we are using our partitioning function and we are putting them into the different reducers, in the each reducer processing, we can basically process them by the increasing order of the key values, so that we are maintaining an order within each partition. But across partition, ordering is not guaranteed. Now there is also one performance improvement that was done, which is of combiner functions. So earlier we had an example of a word count. So let's say we have two different machines, machine 1, machine 2. Machine 1 is creating these intermediate values, A1, B1, A1, and machine 2 is also doing that. Now let's consider that we have hundreds and billions of files, and for each file have around thousands of words, and a word can occur multiple times in a particular document. In what are we doing here is that we are saying A1, we are seeing A1, and now we are seeing A again with just count 1. So, and then we are passing all of this information, we are basically storing them on the local disk first. So it will be stored this way. Then we will pass this information to the reducers. The reducers will read this data over a network call. So as you can imagine that the amount of data that we are sending over a network call is quite high. And we can simply reduce this into an A1, we can say A2. That semantically it would mean the same thing. So that is what the job of the combiner function is. So we can put a combiner function after the mapper and before the reducer that will take this word, and this will be done by offline. That means it will be done locally. It will basically group them by the key and now this data will go over the network to the reducers. So we are getting a lot of this. Basically speeds up the this speeds up the operations for certain MR operations. So this is basically very helpful when we have millions and billions of documents and we are processing them on a very large scale. And this is all in this particular video, and you can read more about it in the paper. We'll share the link of that paper in the description of the video. Thanks for watching.